Okay, the second talk in this morning will be given by Hosho Katsura from University of Tokyo. And he is now going to tell us about constructing frustration-free models via Witten's conjugation. So please start.
Okay, thank you, Chairman. And first of all, I'd like to thank the organizers for inviting me to this really wonderful workshop. So it's a great mixture of people from different fields, so I really like it. And what I'm going to talk about today is something between high energy and condensed matter physics, as the title suggests. And it has something to do with quantum information, I hope. But I have to admit that it has almost nothing to do with quantum extreme universe. So I must apologize for that. But it would be great if someone could come up with the idea to rewrite my talk with extreme universe. So maybe you can tell me at the end of the talk. So I'll be happy. And anyway, so this work was done in collaboration with Dirk Schurich from Utrecht University in the Netherlands, and his ex-student, Julian Wouters. And Julian is kind of a famous guy in the Netherlands because he was a previous champion of javelin. You know, it's yarinage in Japanese. And this is a quote from Dutch version of Wikipedia. So anyway, this is just fun stuff. And my talk will be based on our paper published in Cypos last year. And you can also have a look at the archived version. It's actually better because in the published version, there are some typos, but I have corrected them in the archived version. Okay, so here's the outline of my talk. And in the first part, I'm going to give some brief introduction to exactly solvable models. And after that, I will introduce the notion of frustration-free systems. And then I'm going to move on to the second part, and I will try to explain what the Witten's conjugation is. And then in the third part, I will take you through several examples and try to convince you that this conjugation trick is really useful for constructing many seemingly different models from a simple model like a classical Ising model. And if time allows, I'm going to also touch a little bit on what I call super frustration-free systems, some supersymmetric generalizations. Okay, so exactly solvable models are kind of jewels in theoretical condensed matter physics because they are rare and they are somewhat artificial, but they give us a lot of useful insight about what's going on in more realistic but complicated systems. And roughly speaking, you can classify exactly solvable models into two categories. And the first one is called integrable systems, like free fermions, free bosons, and more intricate Bethe-Ansatz solvable models. And they are characterized by many conserved charges. Commuting with the Hamiltonian, the number of which grows with the system size and could be infinite in the infinite system. And because of this, the dynamics of integrable systems are highly constrained. And the second category is frustration-free systems. In these systems, the ground state is a state such that it minimizes each local Hamiltonian independently. And in many cases, you can get, many-body ground states quite explicitly, but in most cases, it's hard to obtain excited states. And of course, as I said, this is just a crude classification, and these are not exclusive. For instance, the very first example of quantum integrable system, that is the S=1/2 ferromagnetic Heisenberg chain, is integrable and frustration-free at the same time. And yeah, I'm going to explain it in more detail later. But anyway, so here's today's subject. And I will show you a systematic way to construct frustration-free models. And the key to the construction is Witten's conjugation, originally discussed in the context of supersymmetric quantum mechanics. But it's also really useful in non-supersymmetric but frustration-free systems. Okay. Okay, let me start with some rather elementary stuff. So let me run through a crash course in inequalities. And I think these days people are quite familiar with these inequalities and bounds, but just make sure that everybody is on the same page. So let me start with this. And there's a very nice review about positive semi-definite operators in one of the appendices of Hao Tasaki's paper about Hubbard model or his book. But in any case, so let me explain what they are. So let H be finite dimensional Hilbert space, or you can think of it as a finite dimensional vector space. And let A and B be Hermitian operators acting on H. And here are two definitions and definition one. And we write A is greater than or equal to 0 and say A is positive semi-definite or PSD for short if the expectation value of A in any state psi is non-negative. And definition two, so we write A is greater than or equal to B if A minus B is positive semi-definite. And important lemmas just follow from these simple definitions. And first, so A is positive semi-definite if and only if all the eigenvalues of A are non-negative. So you can easily prove this by just considering the spectral decomposition of A, right? So lemma two, so let C be an arbitrary matrix acting on H, then C dagger C is positive semi-definite, right? And one nice corollary is a projection operator is positive semi-definite because you can write P equal P dagger, and you know, because this is a projection, P is P squared, so you can write it P equal P dagger P, right? So it's a positive semi-definite operator. And finally, so if A is positive semi-definite and P is positive semi-definite, then the sum of them is positive semi-definite. Okay, so now we are ready to introduce the notion of frustration-free systems. But actually, the idea dates back to some old paper by Anderson in 1951. So actually, this is just a half-page paper. So the life was easy at that time, right? So unlike these days, people didn't have to write lengthy papers. But anyway, the paper is short, but it's really insightful. So let me explain what he discussed in his paper. So here by H, I mean the total Hamiltonian and consisting of small h sub j. And these are local Hamiltonians, or you can think of it as a sub-Hamiltonian. And each sub-Hamiltonian satisfies this inequality. And this just means the lowest eigenvalue of Hj is Ej upper 0. And then you see that the ground state energy of the total Hamiltonian is lower bounded by the sum of the ground state energies of sub-Hamiltonians. This just follows from a simple variational argument. And what Anderson did in his paper is to just use this inequality and get a lower bound for the ground state energy of the antiferromagnetic Heisenberg model. And interestingly, what he used in his paper is something like a Heisenberg model on a star graph. So this reminds us of the previous talk, right? So she talked about a lot about these geometries. So anyway, so now we are ready to introduce the frustration-free systems. And frustration-free Hamiltonian refers to the case where the equality holds here. And here's a more precise definition. And this H Hamiltonian, which is a sum of Hj, is said to be frustration-free if there exists a state psi such that Hj psi is Ej not psi for all j. So I mean the psi is a simultaneous ground states of these individual sub-Hamiltonians. And there are many known examples, but perhaps the most famous one is S=1 perfect Kennedy-Liptasaki chain. And here is the local Hamiltonian of the AKLT model. And another interesting and famous example is a toric code in 2 dimensions considered by Kitaev. And actually, I think in the audience, there are many high energy people, field theory people. And I think, the field theory counterpart of these frustration-free systems are deficit field theories. So, but because my talk has to do with something quantum information, so let me take a quantum information example. So you can actually construct a parent Hamiltonian of the cluster states. Cluster states are also the subject of the previous talk. But let me start with a trivially solvable Hamiltonian. And so here by x, y, z, I mean parity operators on site J. And by 0 and 1, I mean local basis of, that diagonalizes the z operator. And by plus minus, I mean local basis diagonalizing x operator. And here's our Hamiltonian of the trivial model, which is a sum of 1 minus xj. And because the eigenvalues of xj is either +1 or -1, the eigenvalue of this guy is 2 or 0, right? So this means, each summand is positive semi-definite. So the total Hamiltonian is positive semi-definite as well. And this is just Hamiltonian with magnetic field in x direction. So you can easily guess the ground state, right? And the ground state is just a product state, and every spin is pointing in the plus x direction, right? And there is no entanglement. However, you can cook up a more non-trivial model starting from this trivial Hamiltonian. And that's what people call the cluster model, first considered in this paper. And the Hamiltonian looks like this. So it looks much more complicated than this one because you have 3 spin interactions, right? For neighboring sites, 3 neighboring sites. But actually, these 2 Hamiltonians are related to each other by this unitary transformation. And so, yeah, I'm not considering a ring geometry with periodic boundary condition. And this unitary transformation is a product of these control Z operations for neighboring 2 sites. And so CZ acts on the neighboring site with A, B states like this. So if A and B are both 1, then you get a sign factor. But anyway, so you can verify that these 2 are related to each other by the unitary transformation by some straightforward calculation. But actually, the ground state is quite interesting. Yeah, you can easily get the ground state of the new model by just acting with U on psi. But in contrast to this simple product state, this ground state is entangled. So, and that's why people think that this state is a resource state of measurement-based quantum computation. So yeah, this state is great. On the other hand, mathematically speaking, these 2 are just unitarily equivalent. The difference is just a matter of choice of basis, right? And what I'm wondering now is if we can do something beyond unitary. If there's something beyond the unitary that relates 2 distinct models in a more non-trivial way. And the answer is yes, and that's what I'm talking about today. Okay, so now let me move on to the second part. So I'm gonna first review what the n=2 supersymmetric quantum mechanics is. And then after that, I will show you that the 0 energy states are in 1-to-1 correspondence with the cohomology classes of Q operator. And then I will apply the idea of Witten's conjugation to non-supersymmetric but frustration-free systems. Okay, so I think most of you are familiar with, high energy people are familiar with n equal to supersymmetric quantum mechanics, but let me just briefly review what it is. So here's the algebra of n equal to SUSY quantum mechanics. And Q and Q dagger are called supercharges, and they are nilpotent. That means, they square to 0. And they anti-commute with the fermionic parity operator, which I denote by -1 to the f. And Hamiltonian is the anti-commutator of Q and Q dagger, so which means QQ dagger plus Q dagger Q. And from these commutation relations, you can see that Hamiltonian commute with QQ dagger and the fermionic parity. And many interesting properties just follow from this simple algebra. And first of all, so the energy, any energy, eigenenergy of Hamiltonian is non-negative because the Hamiltonian is positive semi-definite, right? Because of this form. And positive energy states come in pairs because, Q dagger commutes with the Hamiltonian. And the eigenenergy is 0 if and only if a state is a SUSY singlet. And what I mean by SUSY singlet is a state that is annihilated by both Q dagger and Q. And this is just a terminology, but if the ground state energy is exactly 0, then it is said that SUSY is unbroken. On the other hand, if the ground state energy is positive, then it is said that SUSY is unbroken. And interestingly, 0 energy states, if exist, are in one-to-one correspondence with non-trivial cohomology classes of this Q operator. And here's a brief proof. So any 0 energy state, say psi, is annihilated by both Q and Q dagger. But this state psi cannot be written as Q phi for any phi, because this would imply that the norm square, which is psi times Q dagger phi, is 0 because, we have assumed that psi is a 0 energy state. And this means that the 0 energy states are in one-to-one correspondence with equivalence classes of kernel Q over image Q, this quotient space. And this means that the number of the 0 energy states is the same as the dimension of this quotient space. And okay, so here's the Witten's conjugation introduced in his paper in 1982. And you can actually consider some deformation of Q this way. So by M, I mean an invertible operator, anything is fine. And here are new supercharged and Hamiltonian. So new supercharge is defined by the conjugation of Q by M, so MQ, M inverse. And from this new Q tilde, you can construct a new Hamiltonian. And you can actually prove that the dimension of this quotient space is the same as the dimension of this original quotient space. So the proof is a little bit too complicated, so let me skip it. But anyway, physically, what is important here is that this deformation doesn't change the number of 0 energy states. So now let me apply his idea to non-supersymmetric but frustration-free systems. So it's actually kind of easier because we don't have to worry about the supersymmetry here. So okay, so let me first introduce a universal form of frustration-free systems. So without loss of generality, you can set the ground state energy to 0, right? And here's a universal form of the Hamiltonian, which is the sum of Lj dagger Lj. So it's a sum of positive semi-definite operator. And a 0 energy ground state is a state such that it's annihilated by OLJ, Lj for any j. And the question now I want to address is, can we cook up a new model from this known given model? And the answer is yes, and you can actually use the idea of the conjugation. And here is a recipe for the construction. And you can define new L operators from the old ones this way. So Lj tilde is M Lj M inverse, and this M is some invertible operator. And by this Lj tilde, you can define a new Hamiltonian H tilde, which is sum of Lj tilde dagger Lj tilde. And clearly, you can get zero energy ground state of this new model from the older one because, psi tilde, which is M times psi, is annihilated by Lj tilde because of the cancellation between M inverse here and M here, right? And so interestingly, this H tilde is inequivalent to H unless M is unitary. So M is unitary, then M inverse is M dagger. So I mean, these are unitarily equivalent. However, for non-unitary M, these the spectra of these two Hamiltonians are in general different. And however, what is interesting here is this H tilde and H have the same number of ground states. And actually similar idea happened in the very old context of the stochastic processes and called Doob transform. And now let me discuss a little bit more general way to define a new Hamiltonian. But actually, you can freely insert a positive definite operator Cj between Lj tilde dagger and Lj tilde, because it doesn't change the ground state manifold. So this is let's say, newer Hamiltonian in which you have a central term between Lj tilde dagger and Lj tilde. But this doesn't change the ground state, right? Because, these states are annihilated by each term. And okay, so here's a theorem. So let psi k be linearly independent zero energy ground state of H. And k runs from 1 to n, and the ground state manifold of H tilde is given by the linear span of these states, m psi 1, blah, 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 m psi n. And thus, the ground state degeneracies of H and H tilde are identical. And proof is just an elementary exercise of linear algebra, so I want to skip it. But this just follows from, by proving that this space is included in the intersection of these kernels and vice versa. Okay. Okay, so now let me move on to the third part. But before that, any questions from the audience? Okay, so let me move on to the third part. So I will take you through several examples and try to convince you that the method I presented before is quite useful. So I'm going to first show you the example from the classical Ising model. And after that, I will show you some other examples. Okay, so to fix the notation, let me start with spin chain, spin 1/2 spin chain of length n. And the entire Hilbert space is C2 to the n. And by 1n sigma x, sigma y, sigma z, I mean identity and parity matrices. And by sigma j alpha, I mean spin operator as size j. So more precisely, this is a tensor product of 1 and you have sigma alpha at the jth point, and clearly sigma j alpha squares to 1. And by up and down, I mean local basis of sigma z, diagonalizing sigma z. And okay, so here's a Hamiltonian of the classical Ising chain with open boundary conditions. And I have added constant too, so that the local Hamiltonian is positive semi-definite. And this is diagonal in x basis, plus minus ket. And you can factorize local Hamiltonian this way: Lj dagger Lj, and Lj and Lj dagger are the same. They are Hermitian, and they are sigma jx minus sigma j plus 1x. And this is just a classical model. You can easily get the ground states. The ground states are psi plus minus, and psi plus is a state in which all the spins are pointing in the plus x direction, but for plus psi minus, you have spins pointing in the minus x direction. And this is a trivial classical model, no entanglement, no quantumness. However, you can construct a more non-trivial model using conjugation. And here I take M operator in this form. It's a diagonal operator. I mean, the tensor product of 2 by 2 diagonal matrices, and R is some real number. And this is our new Hamiltonian. And this Lj tilde is M Lj M inverse, the conjugated Lj. And after simple calculation, you will get, the explicit form of Hj tilde 1. And you see this term consists of XX term, YY term, and the magnetic field term and constant. And these parameters, Jx, Jy, B1, and epsilon 1 are related to the original parameter R through this relation. And this is actually the XY chain Hamiltonian in the magnetic field, and this model can be mapped to free fermion chain. So it's kind of easily solvable model. And from this construction, it's clear that the ground states are given by M multiplied with psi plus minus. So in real space, it looks like this. So this is just a tensor product of up plus minus R down. And this actually reproduces all results obtained in the 70s by Barocci and McCoy. And you can also prove the presence of an energy gap above the ground state for all R by just using some free fermion method. But anyway, so this is just a free fermion model. So what I wonder now is if we can get something beyond free fermions. And the answer is yes. And you can actually cook up a more complicated model by using a sandwiching method. And here I take center operator Cj to be of this form. So it's almost like an identity operator except for the site J and J plus 1. So here we have some modification, but inserting this Cj between the Lj tilde dagger and Lj tilde in the previous page, you will get a new Hamiltonian, Hj tilde upper 2. And in this Hamiltonian, you have XX term, ZZ term, and the magnetic field term and the constant. And this is what I call the XZ Hamiltonian. And actually, combining the result in the previous page, you can get the XYZ Hamiltonian because, this, HXY in the previous slide and HXZ here share the same ground state, psi plus minus tilde. But that means, this Hamiltonian, which is a linear combination of HXY and HXZ, also shares the same ground state as long as these alpha 1 and alpha 2 are positive. And in this Hamiltonian, you have all the terms XX, YY, ZZ, and magnetic field. And this result reproduces, again, the known result in the 80s. But one bonus here is you can actually prove the presence of the energy gap in this model because, this follows from the minimax theorem in linear algebra. And because the gap is non-decreasing function of this parameter alpha 2, so the presence of the energy gap in HXY implies the gap in the new model. And okay, and actually in one spatial dimension, you can express spin 1/2 operators in terms of fermions via Jordan-Wigner transformation. Here's explicit definitions of Jordan-Wigner fermions in terms of spin operators. And these C and C dagger obey canonical anti-commutation durations. And by Nj, I mean the number operator of these fermions. And you can actually rewrite my XYZ Hamiltonian in terms of this C, C dagger, and N in this way. And it turns out that this Hamiltonian is the same as the Hamiltonian of the interacting version of the Kitaev chain. Kitaev chain is also quite popular in the quantum information literature, right? But the point is, in this Hamiltonian, you have T, delta, mu, U, 4 parameters, but they have to satisfy this frustration condition. I mean, in this particular model, these parameters should satisfy this condition. So, and in which case you can get the ground states explicitly. And in terms of these fermions, the ground states look like this. So these are, superposition of fermionic states with different fermion numbers. So it's kind of a BCS-like state. Now let me move on to a bit more complicated model, ferromagnetic Heisenberg chain. It's something next to the classical Ising model, right? And again, I want to consider the chain with open boundary conditions. And by this both sigma j, I mean the vector consisting of sigma jx, sigma jy, sigma jz. And clearly this model has SU2 symmetry, which means that the Hamiltonian commutes with the total spin operators. And here alpha is plus minus or z. And you can actually write this Hamiltonian as a, projector times constant. And here by singlet, I mean spin singlet state formed between sites j and j plus 1. So by the way, so this one is just added to ensure that the Hj is positive semi-definite. So it's not that important. And the one trivial ground state is the all up state in which you have up spins, all over the sites. And, this state is, this state is orthogonal to spin singlet everywhere, every pair, every neighboring pair, right? So it's a zero energy state of each local Hamiltonian. So this is a ground state of H. And since the Hamiltonian has SU2 symmetry, you can generate other ground states by just acting with S total minus on or up state again and again. And you can actually prove that these states are unique in each total SC sector by using Perron-Frobenius theorem. And above the ground state, you have a gapless spin wave excitation, the gap of which is proportional to 1 over n squared for the system size, large system size n. Okay, now let's consider a deformation of this simple model, just a ferromagnetic chain, into a Q-deformed Heisenberg chain. And so this is, you can factorize the local Hamiltonian this way. So Lj is an operator leads to the transition between a single state to the product of up and down. And as an M operator, I take this diagonal matrix, but it's kind of more complicated than the previous one in the Ising model because the local operator, depends on the site J. But anyway, this is just a diagonal matrix. And you can actually, check that this conjugated operator is written like this. So this part doesn't change, but this singlet Bura is replaced with sing Q, by which I mean Q deformed singlet. So you have, parameters here, right, in front of up, down, and down, up. And so by a straightforward calculation, you will get the modified Hamiltonian Hj2, and it's actually a Hamiltonian of XXZ chain with boundary magnetic fields. So this is the local Hamiltonian, and you have XX term, YY term, and ZZ term, but this coefficient is different from 1, except when Q equal 1. And you have this some kind of stacked alternating fields, but if you add them up, some cancellation occurs, but you still have anti-parallel boundary magnetic fields at the left and right edges. And it turns out that this Hamiltonian is what people call UQSL2 symmetric XX chain in the more mathematical literature, and it was studied in these old papers. And as I said, from the construction, you can easily get the ground state of this new model. And you can actually consider the conjugation of the lowering operator. And interestingly, this lowering operator, conjugated one, is not an element of UQSL2 algebra. So here, sigma j minus is a lowering operator site j. But you can actually get ground state by acting with this modified lowering operators again and again. And here's a proof. And because, M multiplied with O up state is proportional to O up, you can get other ground states this way. And these are actually not orthogonal, but sorry. Yeah, I was saying something wrong. So they are orthogonal, but these are ground states of HXSE and unique in each total SC sector. And so interestingly, they are generated by this. They are the same as those generated by the lowering operator, which is in UQSL2 algebra. So actually, if you usually people need to go through some quantum group book or something like that if you really want to know what the UQSL2 is. But for this model, the ground state of this model, you don't really need to do that. Actually, you don't need UQSL2 here. You can just use this modified lowering operator. And concerning the gap and excited states, you can actually prove that the energy gap is lower bounded by this number. So except for Q equal 1, it's gapped. It's a gapped model. So let me briefly introduce a little bit related model, which is called the Fredkin spin chain. And this is the Hamiltonian of the model. Again, I'm considering spin 1/2 operators on the open boundary chain. And you have boundary and bulk terms, and the boundary terms looks like this. So this is the sum of projections at left and the right edge sides. And the bulk terms are, you can think of them as Fredkin gates. So these terms lead to the resonance between up, up, down, and up, down, up, and this kind of transition. And interestingly, you can write down the ground state in a rather explicit form. And it's actually a superposition of all Dick paths. So let me explain what the Dick path is. So here, I identify up step with up spin and down step with down spin. And the Dick path is a path such that it starts from the left hand side and ends at the right hand side, but they never go below the horizontal axis. And this is the definition of the Dick paths. And interestingly, the ground state of this complicated model is equal weight superposition of these Dick paths. And this data has showed some interesting entanglement behavior. It's actually the entanglement of the half system grows logarithmically with the system size, and the energy gap is parallel in the system side. And you can actually use the same M in the previous page and then reproduce deformed models of the Fredkin chain. And so, yeah, they have some interesting properties, but let me skip it here. And so finally, let me show you some other examples. As I said, the S equal 1 AKOT chain is kind of the most prototypical example of the frustration-free systems. And the Hamiltonian is like this, and it's a sum of, projection operators to spin 2 states. So, let's consider spin 1 chain with open boundary conditions, and this operator projects the states at sites j and j plus 1 onto total spin 2 states. And the ground state can be written as a matrix product state, and you can prove that it's gapped. There's a gap above the ground state. And using this M and judiciously chosen some center terms, you can reproduce Q deformed KLT models with UQSL2 symmetry. So again, you don't really need quantum group here, so that's great. And I think people are getting bored of too many models. So actually, this is the main content of our paper, but actually it's more complicated. I wouldn't like to show you the Hamiltonians. But anyway, so by ZN quantum spin models, I mean some natural n-level generalizations of Ising and XY chains. And they are related to parafermions. So parafermions are natural generalizations of Majorana fermions, and they obey these unusual commutation relations. And here omega is a root of unity, nth root of unity. And using Witten's conjugation, you can reproduce many known models in the literature. And more interestingly, we can construct tons of new models. But yeah, as I said, they are rather complicated. So I don't want to show you the Hamiltonian. So you can just go to our paper. So let me now move on to the final part. I think I still have 5 minutes. So I want to introduce the notion of super frustration-free systems. And so first I'm going to explain what the n=1 SUSY algebra is. And after that, I will introduce some particular example that I call Majorana-Nicolai model. Okay, so n=1 SUSY algebra is slightly different from n=2 case that I explained earlier, but we still have fermionic parity operator, which is -1 to the f, and f is a total fermion number. But in this case, we only have one supercharged Q, because in this algebra, Q dagger and Q are the same. But in any case, this Q anti-commutes with the fermionic parity, and Hamiltonian is simple. This is just a Q square. And from this, you see Hamiltonian commutes with the fermion parity and Q. And zero energy state, if exists, must be annihilated by Q, by this construction. And now let me introduce the notion of local supercharge. So let's suppose this Q is a sum of local supercharges, small qj, and assume each qj anti-commutes with the fermion parity. Then here's the definition of super frustration freeness. So this Q, supercharged Q, which is the sum of qj, is said to be super frustration free if there exists a state psi such that qj psi is 0 for all j. So this is the definition of super frustration freeness. Now, let me introduce one particular example, which I call the Majorana-Nicolai model. And by gamma I mean lattice Majorana fermion. It's its Hermitian conjugate goes back to itself, and gamma I and gamma j satisfy these, standard anti-commutation relations. And in terms of these gammas, fermionic parity is defined like this. And you can actually reconstruct complex fermion Cj out of these gammas in this fashion. And here's our model, what I call Majorana-Nicolai model. And supercharges are sum of linear terms in gamma j and trilinear terms in gamma j. So it's rather complicated. And you can actually get the Hamiltonian by just computing Q squared, but it's a bit complicated, so I don't want to show you. Anyway, in the Hamiltonian, you have 2-body terms in Majorana and 4-body terms in gammas. And here's a schematic phase diagram, which I studied with my student, Sannomiya-san, and Fendry and others also studies a bit more general model. And anyway, so as a function of z, you have 2 phases, SUSY unbroken and broken phases. For small enough g, you are in a SUSY unbroken phase. On the other hand, for large g, you are in a SUSY broken phase. And we have obtained a rigorous upper bound on the critical value of ZC. And actually, Fendry found that the model is integrable at g = 0, at which you don't have a linear term. And what we found in our paper is the model is super frustration free at G equal plus minus 1. So let me explain what it is. So you can actually derive the total supercharge Q in this way. And here these small h like this. So H2L minus 1 is local Hamiltonian of a Kitaev chain in a trivial phase. And on the other hand, H2L is a local term of Kitaev chain in a topological phase. And these are actually frustration-free in the previous sense, I mean the Hamiltonian sense. So from this decomposition, you see that the ground states of the Kitaev chain in trivial and topological phases are annihilated by Q. So this way you can easily write down the explicit forms of the ground states of this Majorana-Nicolai model at G equal 1. And you can actually play the same game in different geometries. And here's one example for Shastri-Sutherland lattice. So you can define local Q for each triangles colored by purple. And actually, the ground state of this model is Majorana dimer covering. You have, I mean, the ground state of two-side Majorana model on each dimer. And you can do something similar for a bit more complicated model lattice, which is called a 312 lattice. Anyway, so let me skip it. So, okay, so here's the summary of my talk. So I have reviewed Witten's conjugation in n equal to supersymmetric quantum mechanics. And I have applied the idea to cook up frustration-free systems. And so, yeah, here's the recipe. So starting from the universal form of the frustration-free Hamiltonian, you can construct a new model by considering the conjugation of Lj and inserting center term here. And this simple construction reproduces many known examples like a Q-deformed Heisenberg model. And it also allows for the construction of new models. And there are many future directions. And one thing is I'm wondering is if this conjugation trick helps prove a gap. And actually the presence of gap, I mean, proving the gap in 2D AKLT models is a kind of, you know, hot topics in these days. And there are several papers about it. And so what I'm wondering is if it's possible to map the original 2D AKLT model to some anisotropic version of the model considered by Andreas Krumpa and others. And other applications are like this. So I'm also wondering if it's possible to apply this idea to quantum many-body scarce. You know, in AKLT chains, a few excited states are known explicitly. But so, you know, so far this method is rather limited to ground states, but I'm wondering if it's also useful for constructing excited states. And it also interesting if we could apply the method to dissipative open quantum systems. So thank you very much for your attention.
Thank you very much for very clear talk. Is there any question, comment?
Thank you very much. Very interesting talk. I have a question about the dimensionality of the system. So your conclusion that it's not dependent on the finiteness of dimension. So you can.
So by dimension, you mean by the dimension of the Hilbert space or spatial space?
Yes.
Hilbert space. Oh,
so
it doesn't. Yeah, actually matter. Actually, I didn't emphasize that. But this construction. So for simplicity, I entirely focused on spatially one-dimensional systems. But you can actually do the same thing in higher dimensions. But you are asking the
Hilbert space dimension. So you do not need to consider the finite dimensional space. Finite dimension Hilbert space. So essentially, you can consider an infinite number of the spins, right? To apply this theory.
You mean by the number of spins?
Infinite.
Yeah.
Number
I see. Yeah. But
so
then
invertibility.
Maybe, invertibility becomes a little bit subtle in such a situation, right?
Okay. So I have some reason why I ask this question. So I'm wondering, can you explore the spontaneous breakdown of Suji? So if you consider an infinite dimensional system, then you may treat such a spontaneous breakdown of Suji case. So it may be
Okay, so
interesting.
that's actually another issue. Actually, I mean, there's a subtle thing about the definition of Suzy breaking in infinite systems.
Yeah.
I mean, the naive definition of Suzy breaking is such that the ground state energy is positive, right?
Yeah.
But it could be there could be the case where your ground state energy goes to zero in the infinite size system, right?
Mhm.
So in this sense, a more precise definition of Suzy breaking is like, I mean, you need to consider the ground state energy density, right? That's well defined in the infinite size system.
Yeah.
So this way you can talk about Suzy breaking in infinite size systems. And that's what actually we did in our paper.
Okay. Thank you very
So
much.
in some cases, you can really prove the Suzy breaking in infinite size systems.
So I have two questions actually.
Yes.
So in this case, you transform Lj, which would be local, to some another local vector Lj shifter. So I expect M have some. I mean, suppose this is some gapped Hamiltonian, and M is unitary. Then unitary mapping local operator to be local operator will be classified as quantum cellular automata. So it will be shift or quasi-adiabatic evolution. And I'm wondering if M in this invertibility restriction plus some local restriction, then can we understand or interpret M as some local statistic operation?
Okay, so yeah, that's a very good question. And actually, so in all of my examples, I take M to be kind of a tensor product of diagonal operators, or anyway, so some simple tensor product. The reason is because that retains the locality of the new Hamiltonian, right? And I think you can also consider something a bit more non-trivial by considering M matrix product operator, right? But yeah, actually, I haven't been able to construct non-trivial example, but I expect that we can also use MPO as an M operator. But yeah, in a more general sense, yeah, maybe there would be some more complicated choice of M, but yeah, I'm not very sure. So yeah, that's a very interesting direction, I think.
Thank you. And the second question is also related to some gapped classification of gapped phases. So even M is now invertible but not unitary, still ground state degeneracy doesn't change.
Yeah.
So I'm wondering if this M can overcome the boundary between different topological phases in 2D, but still have the same ground state degeneracy. For example, polycode has four-dimensional, ground state degeneracy, and also Kitaev model's B phase, non-abelian phase has non-abelian anyons, so different phases, but still ground state degeneracy is the same. So they are not unitary equivalent, but I'm wondering if it could be like, of course, it's just a guess, but it could be related by this M.
Yeah, that's actually what I have been wondering. But actually, the subtle point is, the gap is quite fragile against this kind of deformation. For instance, in my example, like Heisenberg chain, the starting point is gapless, but you can make it gapped by using M, right? And you can actually do the other way around. I mean, starting from the gap model, and then if you choose some appropriate M, then you can make it gapless, right? So this deformation actually, I mean, the gap is not robust, right? So so what is nice with unitary transformation is it doesn't change the gap, right, spectrum, but here, M changes. So what I'm wondering is, if we can define some equivalence classes defined by this kind of M, but I'm not sure if it's possible because of this issue, the gap issue.
Yeah, but it would be still nice if you can connect these two different phases. Of course, the gap closes if you interpret M as some continuous transformation, but it also shows some, if related to the first question, if it's possible, then there is local stochastic, not unitary operation that connects these two phases. So
for finite size systems, the question totally makes sense, right? Because you have the same ground state degeneracy, that means you always have a finite size gap between two models. So yeah, but in the infinite size systems, there's a subtle point, right? Yeah, I agree.
Thank you very much.
Okay, so is there any question?
Can I ask a question?
Yes, please, Tasaki-san.
So yeah, this is Hao Tasaki. Yeah, so this is related to the previous discussion. So you said that sometimes this deformation preserves a gap, but sometimes does not. But do you see any criterion? So in case of this Heisenberg chain, I think you did something very, very drastic. Your M was something very non-translation invariant, right? So do you have a feeling that this kind of M preserves gap and this kind of M does not?
Yeah, so yeah, I don't have a definite answer, but actually this Heisenberg model might not be a very good example because, in the Q-deformed model, you have actually infinite ground state degeneracy in the infinite system, right? The ground state degeneracy grows with the system size, but you still have a gap, but it's a little bit subtle to say it's a gapped model.
Yes.
Isn't it? So yeah, so to be honest, I don't have a definite answer.
Okay. Thank you. Yeah, but can't you imagine that if M is sufficiently local and nice that you can, can't you conjecture something like that?
So yeah, that's a good, interesting question, I think. So yeah, maybe we can say something like for sufficiently small deformation, you can preserve a gap or something, right? That's what you are wondering.
Oh yes, or if M is something innocent, looks innocent, translation invariant and local and. Yeah,
but the problem is, this deformation involves both M and M inverse, and the norm of M, even the norm of M is operator norm of M is small. The norm of M inverse could be quite huge, or something like that. So yeah, I have been actually wondering something similar, but so far, all of my attempts have failed. So
okay, thank you very much.
Okay.
I want to ask you about the extensions of this free frustration system to open quantum systems. Like your Hamiltonian looks very much like the non-Hermitian part.
So could you speak up? So
Sorry.
which slide?
Yeah, exactly. That's like your Hamiltonian H looks like the non-Hermitian part of the Leviathan operator.
Yeah.
Like when you try to do extensions to like those kind of non-Hermitian systems, what kind of things you expect, like naively, let's say, like what kind of, I don't know, non-trivial effects might happen to the Levelian gap, or you have any intuition regarding that?
So yeah, I'm not sure if I catch your question, but actually something similar was discussed in open quantum systems. You can consider something like a Lindeblad equation and consider the coherence-free subspace or something like that, right? And in such a system, you have these L operators. These are Lindebladian, right? But and the decoherent subspace is defined by the span of psi. I mean, these psi are annihilated by Lj or J, right? And actually, I mean, you can just consider new Lj by considering the M operator, and in the new model, you can also get your new decoherent free subspace. So this is some kind of straightforward extension to dissipative systems. Actually, yeah, the reason why I use L was because I was quite motivated by the Lindblad stuff. And of course, in the stochastic process literature, people also considered Markov duality or something like that. I mean, for a given Markovian matrix, you can consider its similarity transformation, which also satisfies the, I mean, defining properties of the Markovian matrix.
Okay. And can you extend that formalism to non-Markovian systems? They can count like memory.
Yes, sorry, I have no idea.
Oh, thank you.
So is there any question or comment?
Okay. I have a quick question. If the system is frustration free, such situations we can construct a non-negative sign problem. There is no negative sign problem in quantum Monte Carlo simulation always, or not?
That's not always true, right? Like, I mean, the AKLT model is one example. I mean, if you just use a naive basis, then you have a sign problem, right? But yeah, of course, if you do some non-local transformation, I think that's what Okuni-san and you did in your papers. But after that, you can get rid of the sign problem. But in general, yeah, I think, for instance, in 2D AKLT model, I think you have a sign problem, but I'm not sure if you can get rid of the sign problem.
Yes. Thank you.
Yeah, that's an interesting question.
So you said, so I think so you said that so it is difficult. We can only get the ground state. But so, for example, is it also difficult to study the correlation function, like on 2-point function?
Actually, so the examples I showed you, the calculation of correlation functions are rather trivial because in most cases, you just have kind of product states or matrix product states. So for such states, the calculation is kind of easy exercise. But in general, yeah, maybe that's an interesting question. So yeah, probably there might be some connection between the correlation function in the original model and those in the deformed model, right? That's what you are asking.
Yeah, maybe. So even when we can calculate the correlation function in the original model, so
but in general, calculating correlation function is always quite difficult, right? I mean, except for these simple states.
I see. Yeah, thank you.
Okay. Is there any other question? So may I ask a question? So
Sure.
Yeah, in your mapping, by your mapping, for the case of the quantum spin chain Hamiltonian, like Ising or XY or Permunic system case, of course, the original Hamiltonian has a very simple form. And so the mapped Hamiltonian also has some integrability.
Or not always, right? I mean,
not always.
For instance, the XYZ chain in the magnetic field isn't integrable. I mean, without magnetic field is integrable, but with magnetic field,
but for the case of the integral case, the original system has probably have some infinite number of conserved quantities, and mapped system also has an infinite number.
Yeah, that's right. That's right.
So is there any one-to-one correspondence between the conserved quantity in the original system and the mapped system? So is it trivial by definition of the?
No, I don't think so. I mean, because, you know, if the transformation is unitary, then it's trivial, but because we have you know, something between, I mean, you know, this is not one, so yeah, it's not really trivial. I mean, yeah, but that's a very interesting question. So for for free fermion models, there must be something, but in general, yeah, I don't expect anything like such a structure.
Okay, is there any other short question? So if not, let's thank speaker again.